All right, let's try an example. So blast off here. We're in a rocket that's fired vertically into the air. And we have a function that describes its velocity at time t, where we're measuring in time in seconds here. So our time, or our velocity after liftoff, is given by this function, v of t equal to negative 32t plus 160, and we're measuring velocity in feet per second. All right, so, and we've graphed it here. So this is our velocity function, similar to that graph we were just looking at. So let's find the displacement of our rocket during the time interval from 0 to 8. Well, hopefully we're not traveling in this thing. I mean, going by our graph here, the velocity here is positive, so it's going up, and then we reach, after 5 seconds, we reach a high point, and then we start falling back down to the ground. So we're starting to move back down here. So hopefully this is, maybe it's like a little test rocket or something, or a little model rocket. We don't want to be traveling in this thing. All right, so we want to find the displacement. So the displacement on this time interval from 0 to 8, what does this represent? Well, it's the integral from 0 to 8 of our velocity function. And we can just calculate this directly. So we have our velocity function right here. Oop. So it's negative 32t plus 160. That's our velocity function. So we can just integrate that. Let's fill it in. Let's get our antiderivative. So what's the antiderivative of negative 32t? Well, the antiderivative there is negative 16t squared. What's the antiderivative of 160? It's 160t. And then we're adding here. So we're adding in our antiderivative. That's our antiderivative. And then we're going to evaluate this from t equals 0 to t equals 8. So this is not necessarily our position function, but it's close. There might be, we would have to, if we were going to find the position function, we'd have to figure out a value for plus c. But to find displacement, that constant term, that c term, it would cancel off regardless. So we just get this antiderivative, and we don't have to worry about c because we're doing a definite integral here. All right, so let's plug in. And top number goes in first, so we're going to get negative 16 times 8 squared plus 160 times 8. And then we plug 0 in, and we get negative 16 times 0 is 0. 160 times 0 is 0. So we get a whole bunch of nothing. Doesn't always happen that way, but in this case it does. So what do we end up with? Well, if you were to do this calculation, it ends up being 256 feet. And our distance here is being measured in feet. So just use units where appropriate. All right, so what we've done here, what this quantity represents is, if we're thinking of it in terms of the graph here, we have this region here. So we have this area above. And then we have this other region over here, which is below. And so another way to think of what this value represents is it represents the area for this region minus the area from this region. So this is our displacement over this time interval from 0 to 8. We traveled, the difference between our starting and ending position is 256 feet. And it's positive, so we're still above where we started. So if we have our little diagram here for our object that's moving in a straight line, we had our starting position, and what we're doing here with the displacement is we're just looking at the difference between our starting and our ending positions. So even though if we're looking at this rocket, it went up and then it hit a high point at time, looks to be about time 5 there. It hit a high point and then started falling back down. So the displacement is only measuring this distance right here. And displacement is positive because we're above our starting position. All right, so that was a displacement calculation. Let's try a total distance calculation. Same setup here. We're going to find the total distance traveled by our rocket during this time interval from 0 to 8. So now we don't want to really worry about the direction we're traveling in. We just want to know, well, how much in total, how much distance did we cover? What's our total distance that we traveled? And so for this, what we want to do, it's going to be helpful for calculation purposes to think of it in terms of, well, let's find the area for this region. Let's find the area for this region and just add those two results together. All right, so to help with this, we need to figure out, where do we change direction? Our object is, our rocket's moving around, and we want to know, where do we actually change direction? And we can see that right here at t equals 5. So if we were doing this problem, we didn't have the graph, what we would do is we would want to figure out, where is our velocity 0? So we'd want to find our t-intercepts. Where does the graph cross the horizontal axis? Find the t-intercepts. So we take our function, negative 32t plus 160, and we would set it equal to 0, and then solve this for t. And in this case, we get t is equal to 5. So once we have where our velocity, where our function crosses the horizontal axis here, then we would want to do a little sine chart to figure out, okay, on each of the intervals then, is our velocity positive or negative? So we want to figure out above or below using a sine chart. So we have our interval from 0 to 8. We plot where our velocity or where our function is 0. So we're just trying to, essentially we're going through the same steps that we would do if we were just trying to find the total area under the curve. So we're finding, first of all, where does our function cross the horizontal axis? Then that kind of splits up our interval. So we're interested in the interval from 0 to 8. That splits up our interval into these subintervals. And then we're going to look at, well, on each of these subintervals, is our graph above or below the horizontal axis? So we can see that from 0 to 8, it's positive. It's above. The values of our function are positive. And if you don't have the graph, you can always use test numbers to help you out. So our interval from 0 to 5, pick a test number, maybe like 1. Plug it into the function here. We get 160 minus 32. That's a positive result. That means our function is above the horizontal axis on this interval. And then we could play the same game, go to this interval from 5 to 8. We can clearly see that on this section here, it's below the horizontal axis. But if we didn't have the graph, we could just pick a test number, maybe like 6, plug 6 in, and we'd get negative 192 plus 160. It's a negative value. And so what we want to do then is essentially to find the total distance that we travel, we really want to figure out, well, what is this area here? What is the area above the horizontal axis? And what is this area here? So we really want to find the areas. So the area above is just the integral from 0 to 5. So this region right here. The area of that region is the integral from 0 to 5 of our function, negative 32t plus 160. And if we integrate that, it's going to be the same antiderivative that we got before. So negative 16t squared plus 160t. And we're going to evaluate this from t equals 0 to t equals 5. And if we do that evaluation, what do we end up with? We end up with, I won't go through all the simplifying, we end up with 400. So if we're just thinking pure geometry here, what is the area for this shaded region? It's 400. Now let's think about this section that's below the horizontal axis. So we have this other region here that's below. And the way to calculate that area, the area for that section that's below, it's going to be the integral from 5 to 8 of our same function, negative 32t plus 160. But the fact that this region is below means we have to adjust. And the way we make an adjustment is we negate this. So if our region is above, if we have this region that's above the horizontal axis, to get the area, we just do our regular definite integral. If we have a region that's below the horizontal axis, the way we calculate the area for that region that's below is just do the regular definite integral, but then we adjust for the fact that our function values are going to be negative by putting another negative in front. So we'll have this negative that just kind of carries along. Ultimately, though, it's the same antiderivative. So negative 16t squared plus 160t. And then we're going to evaluate this from 5 to 8. And if we do the evaluation, top number is going to go in first, so we'll plug the 8 in first. You might want to distribute the negative here. Doesn't hurt to do that, just to make the evaluation go a little bit easier. So you'd plug the 8 in first, then you'd plug the 5 in next and subtract. And if you do that, you end up with 144. So I won't go through all the little simplifying there. So the area for this shaded region is 144. So then to get the total area it's really the integral from 0 to 8 of the absolute value of our function. But really the way to think of this is it's just the area above the horizontal axis plus the area below. So we just take these two values that we got, they're both positive, and we add them together. And what do we get? We get 544. So then the total distance that's traveled in that interval from 0 to 8 is 544 feet. So 400 of those units of distance was when our object or when our rocket was moving up. And then the rocket started falling back down. So another 100, it traveled 144 feet in the negative direction. So this 400 right here, we can think of it as being the area for this section that's above. But another way to interpret this is this is the distance traveled in the positive direction. So this is how much our rocket traveled up. And this 144 here, we can think of it as the area for this shaded region that's below, but another way to think of that is this is the distance that our rocket traveled in the negative direction. So, we have blast off. Our rocket's travels up 400 feet, and then it starts slowing down, and then it temporarily stops, and then it starts falling back down. And it travels another 144 feet in the downward direction, and then our time interval's up. And so all told, it goes 400 feet up, 144 feet down, and the total distance it travels is 544 feet. So notice if we had calculated these values before, we could get the displacement from these. So let's go back. Let's go back to our displacement calculation. So for displacement, we got 256 feet. So we said that was just the distance between our starting and our ending position. It was really the area above minus the area below. So it's how much we travel in the positive direction minus how much we travel in that negative direction. So as just a check here, we traveled 400 feet up and subtract off 144 feet in the downward direction. So this 400 feet, this represents the distance we traveled going up. And the 144 here represents the distance in the negative direction. So displacement is the distance we travel in the positive direction minus the distance that we travel in the negative direction. So it's another way to think of it as area above minus area below. The total distance that we travel is just the distance in the positive direction plus the distance that we travel in the negative direction. Or if we're thinking of it in terms of area under the curve, it's the area above plus the area below. All right. We'll try another example just to get the hang of these. And this will help with area calculations as well, because it's finding distance and displacement and total distance very similar to what we're doing for finding the area for these shaded regions. So we'll try another example. We'll see you there.